Hi, everyone. I'm Amanda Costin. I'm a PhD student at Carnegie Mellon University. And today I'll be talking about a counterfactual audit for racial bias in police traffic stops. And this is joint work with my advisor, Edward Kennedy. Okay, so each year the police stop over 20 million motorists or pedestrians. And these stops are the most common point of entry into the criminal justice system. Police officers have a lot of discretion in whether they decide to make a stop. For instance, a lot of motorists might make minor traffic violations like failing to use a turn signal properly, and the police officer has a lot of discretion with whether to actually pull over that motorist. There's concern that implicit or racial bias may affect these decisions to stop. And so in today's talk, we're going to investigate the role of race in these decisions to stop. Okay, so observational data alone won't get us very far in answering this question. And to see this, let's consider a town outside Philadelphia that has a largely white population with only 5% of residents who are Black. But in 2020, over 30% of those who were stopped by police were Black. So it's unclear whether these differences are due to racial bias or if there's a legitimate reason for this. Perhaps there are differences in movement patterns or behavior that can legitimately explain these disparities. For instance, 3/4 of those who were stopped weren't actually residents of the town, so we don't actually know the demographic composition of the population of drivers that the police could have stopped. So ideally, what we want to do is answer this question using an intervention that hides the race of the driver from the police officer. So imagine that the officer has some kind of virtual reality goggles that can obfuscate the race. Now, this might be really hard to implement in practice for a lot of economic, technical, political reasons, but we still might hope to be able to find a natural experiment that approximates this. Prior research by Jeff Grogger and Greg Ridgway posits that darkness casts a veil that makes it harder for officers to see the race of the driver. So then if officers are more likely, they pull over more Black drivers during daylight, all else equal, one might suspect that there is racial bias in the decision to stop. And this veil of darkness hypothesis has started a literature that often models the odds of being of the driver being Black as exponential linear in the covariance X and the darkness intervention A. Now, this begs the question how we should think about darkness as an intervention on driver race. And in today's talk, we're going to answer this using a counterfactual framework. Okay, so let's revisit the ideal but infeasible experiment where we mask the race of the driver from the officer. The counterfactuals we're interested in is whether the driver would be stopped under no intervention and whether they would be stopped under the race obfuscating intervention. Now we can cast this in the language of potential outcomes, writing as superscript A to indicate that the driver is stopped under A. Our feasible experiment approximates these race obfuscating goggles with the dark of night. So now the counterfactuals that we're interested in are whether the driver is stopped under daylight or under the dark of night. Our next step then is to ask, what kind of effect measures should we use to audit for racial bias? And you might think, well, I'm interested in whether a driver is more likely to be stopped under daylight versus darkness. So I can ask about the average, sorry, we'll just go, okay, so is there a pointer? Okay, so this first quantity, if we're just looking at the average difference among Black drivers, one of the things that it may miss is there could be legitimate reasons for that difference to be zero that don't involve racial bias. For instance, there's some kind of violations, like a driver texting while they're driving, that might be easier for officers to see during daylight. So that's why we may want to compare the average risk sorry, can we go back? Thanks. Okay, so that's why we may want to compare the average risk difference among Black drivers to white drivers. And then, of course, we aren't constricted to just look at average risk differences. We can also kind of do the same thing with average risk ratios. And actually, these risk ratios are going to be useful given the sampling design of our data. So now we can advance. So that's that we only observe data for drivers who are stopped. In these administrative stop records, we typically don't have any information about drivers who police did not stop. And so under such a sampling scheme, it's really hard to identify these risk difference type measures, but we can still make progress with these risk ratio type measures. And that's because we can write this ratio of race conditional risk ratios as this odds ratio in the second line. So that's the odds that the driver is Black, conditional on being stopped under darkness, over the odds that the driver is Black, conditional on being stopped under daylight. And we can start to see that, so while our target causal estimand is a ratio of risk ratios, the statistical estimand is going to take the form of an odds ratio. Now, to get the statistical estimand, we need to identify these potential outcomes by controlling for confounding factors like time that can affect driving behavior, the demographic composition of drivers on the road, and darkness. So specifically, we need race to be independent of darkness, conditional on the potential stop outcomes equaling 1 and our measured covariates. And we also need overlap to hold. Then we can write this conditional counterfactual odds ratio on the left in terms of observable quantities on the right. And this connects back to prior work in the Veil of Darkness literature that essentially estimated this quantity on the right. And this is nice because this gives us a causal interpretation of the results of prior work, but also additionally, by starting with this estimand, it opens us up to be able to pursue more flexible estimation approaches than what was previously done. So we might, for instance, want to estimate this quantity using some kind of flexible non-parametric approach, or we may want to aggregate these X conditional effects into a useful population measure. And we'll consider both of those problems. So first, to estimate the X conditional measure, we'll do a simple plug-in approach where we estimate the two nuisance functions that are required to write this X conditional odds ratio. That is, mu1 is the race outcome regression conditional on darkness, and mu0 is the race outcome regression conditional on daylight. We can use some flexible regression method to estimate these and plug those in to get our estimate of the X conditional measure. We apply this method to data from the Stanford Open Policing project, which covers roughly a 10-year period. And we include as covariates the time of day of the stop, the day of the week, and the season. Following prior work, we restrict our analysis to only fall and spring for overlap purposes. Because of the discontinuity of daylight savings starting in the spring or ending in the fall, we can observe daylight and darkness at the same time for different days in the seasons, depending on whether it occurred before or after daylight savings starts in the spring or ends in the fall. Also, following prior work, we restrict our analysis to stops where the driver's race was perceived either to be Black or white. And we look only at stops in the evening, excluding those that occurred between sunset and dusk when it is neither daylight nor dark. So we can visualize some results for the city of Madison, Wisconsin. There were about 8,000 stops in this period, and 1 in 4 of those was a Black driver. And I've used GAMS here to estimate the nuisance functions. The color of, sorry, we can go back, thank you. So the color of the dot corresponds to the value of the estimated conditional odds ratio using our plug-in approach, where red suggests there may be racial bias against Black drivers, white, no effect, and blue suggests that there's a protective effect of daylight for Black drivers relative to white drivers. So these are just point estimates, but this gives us an idea of some of the spread in these X conditional measures. And we do the same thing for several other cities in the US, Fayetteville, North Carolina, Louisville, Kentucky, Pittsburgh, Pennsylvania, and St. Paul, Minneapolis. In here, I've plotted the distributions of these estimated X conditional effects. If we're interested in summarizing these into a population measure, then we next consider the question of aggregation. So a natural starting point would be to compute the expectation of these conditional measures over the observed drivers who were stopped. However, this may not be a good or useful population summary because of the issue of non-collapsibility, which we can see with a simple example. So this is just a toy example, but here the conditional odds ratio is a constant, 1/45, but the marginal odds ratio takes on a different value, right? And so that's this non-collapsibility issue of the odds ratio, but we can actually get around this if we do the aggregation differently. If we aggregate via the geometric mean, that is, we take a product of all the X conditional odds ratios exponentiated to their density, then we can actually recover collapsibility. So back to our example, now the geometric odds ratio is that same constant that we saw for the X conditional effects. So we propose a doubly robust style bias corrected estimator for this geometric odds ratio that's based on the efficient influence function of the log geometric mean, given here as phi. So phi takes a plug-in estimate of the log conditional odds ratios and adds a bias correction term that's inversely weighted by the propensity score and the outcome variances. And under some assumptions on sample splitting, overlap, consistent estimation of phi, and the outcome variances being bounded away from 0, then the estimator has error that's second order in the nuisance function estimation error, yielding doubly fast rates that enable us to estimate the estimator at faster rates than the nuisance functions. So for instance, if we want to estimate, to get root n rates in our estimator, we need only estimate the nuisance functions at n to the quarter rates. And under a non-parametric model, if the nuisance functions are achieving those n to the quarter rates, then this approach is locally minimax optimal. So now let's see what we get in the real world data. Recall that a value less than 1 means that darkness decreases the risk of a stop for Black drivers relative to white drivers. And we see these values less than 1 for 2 cities, St. Paul and Fayetteville. We don't see bias in terms of this measure for the other 3 cities, but that shouldn't be taken as indicating that there is no bias. There could be a number of reasons for this. So perhaps in those cities, there's less of a difference in visibility between daylight and darkness. And additionally, this test won't detect upstream bias in the decision where officers patrol or downstream racial bias that can manifest in the decision to use force, to search for contraband, or to make an arrest. So we are actively pursuing some additional empirical analysis that will include sensitivity analysis to validate these findings and better understand them. At that point, we'll put out a full paper, so stay tuned for that. And now I'll just recap that. So in today's talk, we proposed a counterfactual measure of racial bias in police traffic stops that provided a meaningful causal quantity, that we had a nice causal interpretation for what we're estimating. And this measure is also identifiable under the outcome-dependent sampling. And the measure also connects back to prior work in the Veil of Darkness literature. We propose estimating this using a simple plug-in approach. And then consider the question of aggregation, proposing using geometric mean to maintain collapsibility. Our proposed method for computing the aggregate measure is this bias-corrected estimator that has these nice doubly small error guarantees. And on real-world data, this pointed to racial bias in 2 out of the 5 cities analyzed, but we will expand our analysis to more regions in the US. So thank you so much for your attention, and I look forward to continuing the discussion.